Okay, we'd like to welcome everybody to the May session of our CBRS meeting and seminar, and an excellent presentation in store today, which is the first part of a two-part that will continue on for the next one, the last one before our summer break in June. And this is about vacuum tube television, and we have our resident expert in all things radio and TV, who has had many, many years of experience in dealing with such sets, Don Killips. And so for the next hour, well, it'll be a little bit more than an hour today, maybe an hour and a quarter, perhaps, depending on how this session goes. He's going to take you into a detailed look at vacuum tube television, and at the same time talk about how some aspects of it could be restored without a whole lot of test equipment at your disposal. So this should be very interesting, and we'll turn over the floor and the session to Don. Thanks very much, Don.
Thanks very much, Murray. So we're going to get started with black and white TV. The tube type TV, I won't be discussing any transistorized TV sets. And the tube type TVs that we're most interested in were produced from 1944 until somewhere up around 60. Before 44, there was some reproduced, but not in Canada. They were small, round, oval-shaped screens brought up from the United States, and they didn't work very good because some of the frequencies were changed a little bit in the way those machines operated. But they were compatible. But we're going to start here. We have a diagram here of an AM radio, and you notice it has an RF amplifier. We have one of those in a TV set too. And we have a mixer and an oscillator. And we have an IF amplifier. In a TV set, it may be 2 or 3 stages. Then we have the detector stage, same as in a radio. And we have the first audio and the audio output tube. Well, this is a radio. So there you are. We have 1, 2, 3, 4, 5, 6, 7. Now the TV set has all those stages plus many more. I'm going to put the block diagram on now for the TV set. Okay, we have the RF amplifier, we have the mixer and the oscillator. It may be 2 separate tubes, usually it's just 1 tube. We have the first IF, the second IF amplifier, and the third IF amplifier. You notice we have 3 stages of IF amplifier. That is because we want to have a wider bandwidth, and of course the wider you make the bandwidth, the lower the gain. So we need extra stages to bring up the gain. Some of the newer black and white TV sets cut this down to 2 stages, but they didn't work quite as good. They sacrificed a little bit of quality doing that. And there was a few old ones around, like the Dumont and stuff, that had 4 stages of IF. Here we have the video detector. We don't call it a sound detector, we call it a video detector. And of course, instead of an audio amplifier, we have the video amplifier. which amplifies the signal from the detector the same as it does in a radio, only it's not, in this case it's sending a video signal, not an audio signal. Now at the detector somewhere, or in the video amplifier, the sound is taken off and it's fed back down this way into the first audio IF, which is 4.5 megacycles, and into the audio detector. In some radios, or some TVs rather, they have another stage in here called a limiter, depending on what type of detector they use. Next to that we have the audio amplifier, same as in the radio, and the audio output, same as in the radio, and a loudspeaker. Now you'll notice some other stages down at the bottom here. Well, there's the power supply. Usually puts out around 260 volts, and that supplies all the different stages. Over here you'll see a vertical oscillator and a vertical output. These are running at 60 cycles per second, same as the line frequency. The reason for that was they picked the 60 cycles was so if there's going to be any hum bars on the screen, at least they're going to stand still. They're not going to move up and down. So the vertical oscillator 60 cycles, and the vertical output tube, instead of driving into a speaker, it drives into a yoke on the picture tube. Down here we have a tube called a sync pulse amplifier, and it also clips off the sync pulses from the video information. We'll get more into that later on. Down here we have a horizontal oscillator and a horizontal output tube. That's the big baby that costs lots of money. And of course that drives into the flyback, which is over here, and these are the yokes. Now you'll see that the flyback is connected to the damper tube, and the damper tube is connected to the 260 volt line. But the damper tube is actually across this portion of the horizontal output transformer, and it rectifies it, and it makes a thing called B-boost, which is about 500 volts or more, and it's used to power up this horizontal output tube plate circuit, because this 260 wouldn't be enough to make it work. And of course a horizontal oscillator, the horizontal oscillator frequency, remember these frequencies, I'm doing all this by memory today, no papers. The horizontal oscillator frequency is 15,750 cycles per second. Now we also have a feedback here. Coming from the flyback through a capacitor, or some other method, they use different methods, comes back to a tube or a dual diode or something called the automatic frequency control. And of course the sync pulses run into that, and if the horizontal output tube is running ahead or a little bit behind the sync pulses, it sends a pulse up back to the AGC circuit, which corrects itself. Because the horizontal is very critical. It has to start at the top of the picture. You can't have it starting halfway down the picture. So it has to start right at the top. Not only that, it doesn't start in the left-hand corner of the picture tube. It starts in the center of the picture tube at the top. Your first scanning line starts from the center of the tube and goes to the right-hand side. What else we got on here? We have an AGC circuit. Some of the cheaper TVs they just took their AGC from the detector circuit like they did in radios and fed it back to the IF stages and to the RF amplifier stages to control the gain so the picture wouldn't overload. But the trouble with the TV signal, you cannot do that very good because the video content is changing from a dark scene to a light scene or something in between, and that means the voltage at the detector is going to be changing, and that means your AGC voltage is going to be changing. So it wasn't a good system of AGC. It was developed later on, the keyed AGC circuit, which also takes a pulse from the flyback up into a special tube for the AGC, and that works on the tips of the sync pulses, and they're always at the same level. And we'll come into that when we get around to discussing AGC. So I think that pretty well covers this. The video amplifier, by the way, drives usually into the cathode of the picture tube. Although it can drive into the grid, but it's usually driven into the cathode. And we're going to do a little bit on picture tubes because it's nice to know how they work. And it's nice to know how the scanning lines work and how many they are and so on. You see, when they were developing TV, there was two primary concerns that they had to overcome. One was motion. How many frames do you have to have in a picture to give you motion? Anybody know? Well, 24 will do it. That's right. But for TV we chose 30, which is a little bit better. But motion pictures are 24. And that took care of the motion because your eye has a persistency of vision, which when it sees something and it moves a little bit, it looks like it's moving. It doesn't look like a picture here and then a picture here. It looks like it's moving. Your eye does that for you. So the next thing is flicker. Flicker is like a light coming on and off, and at 24 frames you can see this flicker quite bad. It's very annoying. It's like a 25 cycle power supply down in New York where they had fluorescent tubes trying to go. You know how that worked. You could see them going on and off. So they had to get rid of flicker, and that meant increasing the number of pictures. But unfortunately, increasing the number of pictures would mean increasing the bandwidth. So they come up with some ingenious ideas. First of all, I'll go back to motion pictures. They are sending, in motion pictures, they are sending the whole picture at one time, the whole frame. And we don't do that with television. But anyway, they do in motion pictures. And they found there are shutters on a motion picture camera which close when the film is moving from one frame to another. So you don't see a frame traveling across the street. It's blacked out because the shutters are closed. But some brilliant guy, I don't know who it was, if it was Edison or who, I have no idea, discovered that by making the shutters close, first the picture would slide into place, the shutters would close while it slid into place, the shutters would open, and then they would close, and the picture wouldn't move. And then the shutters would open again, and then close. Then the picture moved. So what it meant was they were showing each picture twice by having the shutters running twice as fast. And that got rid of the flicker in the motion picture business. In TV, we have a little more problem getting rid of flicker. We use a system called interlace scanning, and it works very well too. So I'm going to take this off for now. That's the picture tube right there, and you can see all the different components of it, and this part here being the glass bulb, and the amount of degrees between here and here, it could be a 70-degree picture tube, could be a 90-degree picture tube, or they went to 110 and possibly a little bit more degrees to get a flatter picture tube. And they had to have the surface of the glass curved to withstand the pressure, the air pressure pressing on it when there's a vacuum inside the tube. Now this glass is about a ½ an inch thick because there's tons and tons of pressure on there. If you figure the atmospheric pressure at 14 pounds per square inch, you'll see that it's quite a bit of pressure on that glass. So the glass has to be real strong. Not so much the neck, because the neck doesn't have so many square inches of surface, and it's curved too, so that's helps strengthen it. Now you'll notice inside this picture tube you'll see 2 dotted lines on the front. Well, the one closest to the glass is a layer of phosphorus. P4 phosphorus is used in picture tubes. It gives a white light. There's some other colors for scopes and that have a different number. There's a bit green. Anyway, the P4 phosphorus is applied to the picture tube, and it has the ability to emit light when it is struck by an electron beam. When it's not struck by an electron beam, it doesn't give off any light. So we have in here a device for making an electron beam that goes up and hits on the screen. The newer picture tubes have another coating on the back of the phosphorus, that's this next dotted line, which is called a luminizing. It's a thin layer of metallic compound sprayed onto the phosphor, which brightens a picture quite a bit because the light coming off the back of the phosphorus is lost. Only we see the light that's coming off the front of it. But the light coming off the back of it is lost, but when we put that illuminizing layer there, it's reflected back out the front. So an illuminized tube is quite an improvement over one that's not illuminized. In fact, we used to rebuild picture tubes and we didn't even bother rebuilding them if they weren't illuminized, because usually the phosphor got a kind of an X burn onto it just from general use, you know. So they weren't too good of a tube. And they used to have a thing called an ion trap. Back here at the cathode there was some ions floating around, and they were quite heavy. They weren't affected by the yoke, and they went flying right through to the screen, and they bombarded the center of the screen, and they would chew up the phosphor. So they had the thing called an ion trap. Whereas the gun was actually at an angle like this, and the ions all hit the glass here and dispersed inside of the neck. But they had to have a magnet to re-straighten that beam out to get it going in the right direction towards the picture tube. And that was called an ion trap magnet. Do you ever remember seeing those?
Yeah.
Yeah, okay, well that's what they're for. Now, the idea is to make an electron beam that is as fine and as thin as possible, especially where it strikes the screen, if you want to have a good focus. So, the electron beam is processed back here in the neck of the tube called a thing called an electron gun. And in the electron gun, the first thing you'll see here is a little filament inside of a cathode. And of course the cathode is heated red hot, just like in a vacuum tube. And then next to the cathode we have a grid, which is just a disc with a hole in it. So the only electrons that can get through have to go through that little hole. And this already starts in the shape of a beam. They have to be further adjusted after that. Now they go through the first anode, which is another metal plate with a hole in it, connected to B boost around 500 volts. And that gets the electrons moving away from the cathode at a pretty good clip. And then on the inside of the picture tube bell, not the front, but the bell here, is another coating called Aqua Tank, which is just a carbon-based type of paint on the inside of the glass. And it's connected to where your high voltage goes into the tube at the little, well, we call it the belly button on the side of the picture tube where you connect your high voltage. That goes to the Aqua Tank coating, which is just a conductive paint on the inside of the picture tube. Now that conductive paint has 15,000 or more volts on it, and that attracts the electrons towards the screen too. So it also has another metal disc connected to it here with a hole in it. So, but now we're starting to get an electron beam that is quite small and strong. But we have to have a way of adjusting it, and there's been several ways tried. This is the most common way nowadays, is electrostatic focus. It's just like a little tube here that the electron beam passes through, and when you set the focus voltage up here, you can set it at 500 volts, 250 volts, or 0 volts. Sometimes you got a control, you can adjust it, and you can cause it to focus right at the screen. You don't want it to focus back here or out here, but it doesn't go out there anyway, but you want it to focus right at the screen to the smallest dot you can get. So you always adjust that for fine scanning lines. Try to get your scanning lines as thin as possible. Now you never want to run a picture tube like I got it drawn here without any yoke on it, because the electron beams will all end up here and they'll be so intense they'll burn a hole in your phosphor. So you can't have that. Anytime that you see a electron spot on a picture tube, you got to shut it down immediately. Otherwise you'll ruin your picture tube. The yoke moves the electron beam all over the place, so it's never in the same place for very long. the fact it travels very rapidly. Now we're talking about microseconds. Do you know what a microsecond is? Really? It's a 1/1,000,000th of a second. So it's not very long. And we don't use milliseconds because everything is faster in TV sets.
Too slow.
So the yoke, there's two yoke coils that fit over the neck of the picture tube. I guess everybody's seen a yoke coil. There's the horizontal ones and the vertical ones. The horizontal ones bend the electron spot this way, and the vertical ones bend it this way. The two of them together can make it cover anywhere in the picture tube, right from one corner to the opposite corner. So with the yoke running, it's pretty safe to turn a little bit of brightness up so you can see it, and without burning away your picture tube. Now the older sets used to have to focus it, some of them had a coil which you could adjust the voltage through. They were magnetically focused, and there were some that had permanent magnets. I think RCA Victor used some with permanent magnets. And then there's the electrostatic focus like I show here, which didn't use any magnets. Now, the picture tubes come in different voltages in the filament. Some of them are 6, some of them are 3 or 2 volts, depending on what kind of tubes are used in the TV set. If they're series tubes, it all has to add up to 115 volts or so. And the signal is driven into the cathode, just like in an amplifier tube. It can put bias voltage on the cathode, change the bias voltage on it, and cause the electron beam to get stronger or weaker. And it can cause the electron beam to go black so that it doesn't make any light on the picture tube, or it can cause it to go white and it will trace the white lines on the picture tube. All depending on the voltage on the grid, or on the cathode, pardon me, the driving into the cathode. The grid is fixed. You can drive either way, it doesn't matter. It's just the difference in voltage between the grid and the cathode. If you ground the grid, then you can drive the cathode. Let's try our next picture. There's a picture. This is an exaggerated picture. It only shows 10 scanning lines. The odd ones are on this side, the even ones are on this side. The odd ones are solid lines, and the even ones are dotted lines. So you can see that's the front of the picture tube, and you can see that it starts scanning at the top center of the picture. And it traces down to line number 9 at the bottom corner. There it is retraced back up to the top. It's blacked out so you can't see the retraced lines. And when it gets back up to the top, it starts down again on field number 2. And that's the dotted lines, the even numbers. And when it gets back down to the 10, you notice that it stops in the center of the bottom of the tube. So when it is returned, it's ready to start at the center of the top of the tube. But we have many more scanning lines than this. I've only showed 10 there. But we're running about 488. Actually, it's 525, but some of them are wasted. They're wasted at the bottom of the picture to make a little frame, and they're wasted at the top, and there's some wasted during vertical retrace times, because there's 2 vertical retrace times. Don't forget now, a field, this is a field. The dotted lines is one field. There's 244 and a half of them. And the solid lines are another field. And there's 244 and a half of those too, making a total of 525 lines. And when it's retracing vertically, the horizontal must be kept in sync and still scanning. You can't see it because it's in the blacker than black region, and you can't see it, but it has to be kept running. So that's how we get rid of flicker, by interlay scanning. 2 scanning systems for one frame. These are called fields. There's 2 fields, and there's 60 fields a second, and the 2 fields make one frame. There's 30 frames a second, and the frame has 525 lines. Some of them are wasted, but that's okay. It has to be that way. And you will see that 525 lines times the frequency 30 cycles ends up at 15,750 scanning lines a second. That's the frequency of the horizontal oscillator. Don't forget those horizontal and vertical oscillator outputs feed into the yokes, and they're the ones that are moving that electron beam wherever we want it to. There's some data for you. 2 fields make one frame. One complete field has 262 and a half lines. The second field is 262 and a half lines. Those aren't all active. Some of them are lost at the edges of the picture. One frame has 525 lines. 30 frames per second have 15,750 lines. The frame has about 488 active lines. The remaining 37 lines are used for vertical retrace and a little blacking bar at the top of the picture and the bottom of the picture. One horizontal line, including retrace, is 63.5 microseconds. One line across the CRT without the retrace is about 57 microseconds. So it's moving pretty fast, almost the speed of light nearly. Here's a little diagram which shows you what the sync pulses look like. This is like a video signal right after the detector. We have here the video signal. It can be anywhere, up and down. This would be white, this would be gray, and if it was way up here it would be black. And you notice that the sync pulses are in the blacker than black region. You see that dotted line across here? Well, that's the black region. Anything above that you can't see. And you notice that each sync pulse has a front and a back porch. That's just to help blanking out the retrace lines. Here's a black picture shown here, way up high, almost at the black level. And this is a white picture. This one here is white. So, what we're doing with the TV, we're slicing it up into 525 strips. And we're sending them out one after another. And when you receive them, just like you receive an AM radio station with an antenna, you have to amplify them and detect them and process them to whatever you want them to do. So, and that means putting them back together into a picture. And the picture has to start at the top. You can't start halfway down. You can take the vertical hold and sometimes roll the picture down and bring it back up with the vertical hold. If you got an old set, you'll have a vertical hold. And when it gets to the top, if it doesn't stop, that's because you don't have no vertical sync pulses. And it'll just keep rolling on you all the time. And when the horizontal goes off frequency, it usually gets diagonal lines across the screen. And sometimes you can adjust it with the horizontal hold control. I wouldn't recommend tinkering with the horizontal oscillator coil unless you know there's somebody else that tinkered with it before you. Otherwise, that probably wouldn't be a good idea. It'd be best to find out what else is wrong.